So that's what's going on here. Now, you may ask, where did this come from? Well, remember, this is a cross product, right? So if you take the x component of the angular momentum here, that means you have to take the x component of this. Now, like I say, assume you've done enough vector calculus to know what the x component of that is. Well, it'll be y pz minus z py. I'm mixing z's and z's. I've lived in 3 English-speaking countries, okay? Right? So, if you forget the hats, just think ordinary classical mechanics. Then L of x is just y pz minus z py. Right? That's just as a result of the cross product. But now we're thinking quantum mechanics, and we're going to put a hat. We're going to convert each of these physical quantities from classical mechanics. We're going to make them now operators in quantum mechanics. And you may ask, well, why is that justified? Why are you doing that? Well, it's sort of using the correspondence principle, right, of Bohr, and the usual answer. It works. Now, if something hopelessly didn't work, well, you wouldn't be hearing about it, right? It's part of a course. You get, especially at undergrad level, you get presented with stuff that works. Yeah, just think of the psychology of education. All right. So okay. So without the hats, these 3 here are just the standard x and y and z components in x, y, and z directions along the x, y, and z axes, if you like, according to classical mechanics. Now we put a hat over all of them. We convert each of these terms here now into quantum mechanical operators. Right? Now, the y psi, the wave function, is just y, the eigenvalue, just the value of the position, if you like, of y psi. So this y hat will correspond to this y eigenvalue, and p hat is minus I h bar d b d, or whatever this is, dz in this case. Right? From previous lecture, previous chapter, chapter 6, you know what the quantum mechanical operator is for momentum, right? It's minus I h bar d b d. Well, we did d b dx, talking 1 dimensions, but now we're in 3 dimensions, right? We're in angular momentum, so we've got rotation and all that sort of stuff. So we're not on a straight line. We're not on an axis. We have to be in 3D. Okay. All right. So the quantum mechanical operator for momentum along the z-axis would be minus I h bar d b d z, right? And similarly for y, so you'll have dy. And the position operator for z, its eigenvalue will be just z, right? So the x component of the angular momentum operator is this, okay? And similarly for the y component of angular momentum operator, this, and so on for z, okay? Now, here's yet another instance of the use of vector calculus. And I've already decided I will teach a course. I'm not quite sure yet whether it'll be a full course or a mini course on vector calculus, because it keeps getting used in this quantum course. Now, this here is using the coordinate system of Cartesian coordinates, just x, y, and z. The x-axis, the y-axis, and the, say, the z-axis heading towards the camera. Now, an alternative, well, there are many coordinate systems. Right? An alternative to the Cartesian coordinates, x, y, z, where you need 3 numbers to isolate a point in space, its coordinates. another very commonly used coordinate system is the spherical polar coordinates, in other words r, theta and phi. So r is, so if you have a, well, let's say that's the z-axis, and the y-axis is that way, and the x-axis is that way, and you have a point out here in space. Okay? R is the distance from the origin is just here. R is the distance to the point from the origin, and theta is this angle from the vertical, that's theta, and phi is the angle from the y-axis to the direction of that point. Like if you project the point down to the what am I projecting? So what did I say that was? Did I say that was y? Okay, so the yx plane. So project that point down to the yx plane, and then theta is the angle from the y-axis to that point on the xy plane. So it's that, I don't know if you can see this in the camera, that's phi. So r, theta and phi, the spherical polar coordinates. Now we will use that r, theta, phi coordinate system, the spherical polar coordinates, because it's more, that particular coordinate system is more useful than the Cartesian coordinate system, x, y, z, because we're talking about things rotating, right, and moving around in 3D space, because we're talking about, you're in the context of angular momentum. So for example, if you had a system that had spherical symmetry, and imagine some particle that's spinning around a nucleus or something, and its radius is constant, well, it would be much more convenient to use the spherical coordinates, right? R, theta, phi. You just describe its motion as r, the radius is constant. It's so much easier than describing it using x, y, and z, because if it's rotating, the x, y, z's are changing all the time. But using r, theta, and phi, you can express the dynamics, the behavior of the system much more easily. I hope you see that as intuitively obvious, right? Because for this chapter, we're going to be using spherical polar coordinates, r, theta, and phi, for that reason. Now, you can find expressions for the x, y, and z coordinates, x, y, z, in terms of r, theta, and phi. Well, I'm assuming you've done vector calculus, so you would know how to do that. I mean, I'll give you one, for example. The z component is r cos theta, and the x and y are a bit more complicated. They involve angles, the theta and the phi, but I assume you know how to do that. Now, towards, from memory, it's been a while. I will give this course on vector calculus, and from memory, I can remember towards the end of the book, there were more complicated expressions like what's the equivalent of y dz minus z dy if you're talking in spherical polar coordinates, r, theta, and phi, and the answer to this is this. Now that may seem fairly complicated, and I'm just throwing it at you, and the textbook does as well. It's also assuming that you've done some vector calculus. But for those of you who haven't, this will just be a complete mystery. You won't know where it's come from. So just out of a sense of completeness, I feel increasingly the need to give this vector calculus course. So I will do that. I just haven't decided yet whether it'll be a full course or a mini course. All right. Well, if you don't know where this comes from, you just have to accept it. But since you can convert x, y, and z the coordinates into the equivalent coordinates in terms of r, theta, and phi, you can find the equivalent of r dz minus z dy in terms of r theta and phi, and you get this, right? And there'll be something similar for Ly that run out of, well, you may, I'm not quite sure if you can see it, but there'll be something similar for Ly and Lz in terms of the operators. The x component of the angular momentum operator, L hat, okay? And similarly for Ly hat and Lz hat. But that will be for the next session.